All right, let's get started again. This is hour 3 for Physics 1B for November 16th. And we're continuing to talk about entropy and the second law. So I pulled these pictures up here. We can talk about them just briefly. When firecrackers explode, this is a picture of an exploding firecracker, apparently held on a stick or something. I don't know what's going on here exactly. But there's a combustion of a firework that's been captured with a camera. And the neatly packaged chemicals within each firecracker are dispersed in all directions, and the stored chemical energy is converted to random kinetic energy of the fragments, right? That's an example of entropy increase, and then we kind of talked about this during the break, but diffusion is also an example of entropy increase. You never see processes where a firework suddenly kind of goes backwards and becomes a firecracker again. You can take a video of it and then run it in reverse if you want to, but that's not reality. That's just likewise, you would never see dye unmix and go back into the system. If you take a glass and you knock it off a table and it shatters into a bunch of pieces, it would be quite difficult to get the glass to suddenly and spontaneously turn back into just a glass. Although, if you have something like a coffee cup and it breaks on the ground and it only shatters into like 2 or 3 pieces, you could obviously, with a little work, put it back together again if you want to, but it just wouldn't happen spontaneously. And that's the idea of what entropy is and why it is that when all systems are taken into account, entropy increases or remains constant. In reversible processes, the entropy might remain constant, but in any irreversible process, the entropy will definitely increase. All right. So let's look at some problems where we can do some calculations with entropy so we can actually see how you truly can quantify it. I didn't say, but the units for entropy are going to be joules per Kelvin. Right, because Q is heat and T is temperature, so joules per Kelvin are going to be the unit of entropy. Okay. I know we kind of already said this. Maybe we don't need to read that part. I just thought there was a description in your book. Now we're going to do this one and this one. Do this one as well, and we're going to do this one too. I don't want to spend the whole rest of class just doing problems. I do want to talk about microstates before we finish today. So if this is taking a little too long, I might cut one of these problems short. Why doesn't it just paste it right here? I don't, or maybe it didn't. I'm being, okay, it did. Okay. We'll just shift these down a little bit as we do these problems. Okay, entropy change in melting. What is the change in entropy of 1 kilogram of ice that is melted reversibly at 0 degrees Celsius and converted to water at 0 degrees Celsius? All right, I don't know how you would reversibly melt ice, but there it is. So our definition of entropy change in entropy, is equal to, there's no temperature change in this case, is there? So I think we can just do, for this one, I think we can just do Q over T for this one. Where the Q in this case is going to use the latent heat of fusion, so it's going to be the mass of the water times the latent heat of fusion of water divided by the temperature. I don't think we need to break this up into infinitesimal processes. I think we can just do this. So this is going to be 1 kilogram multiplied by 3.34, looks like a 9. .34 times 10 to the 5th joules per kilogram. And then we would divide by the temperature, which is, it looks like 0, but it's not really 0, it's actually 273 in Kelvin. Okay, so we calculate that. We get 1,223 joules per Kelvin. That is the change in entropy for this system. Very straightforward because the temperature is constant. Now, when the temperature is changing, Gets a little trickier. Okay, so here's a problem with the temperature change. So now what we have is 1 kilogram of water is at 0 degrees Celsius is heated to 100 degrees Celsius, and we want to compute its change in entropy. And we're going to assume that the specific heat of water is constant at 4190 joules per kilogram Kelvin over this temperature change. I usually don't include these things because I think it takes away some of what's going on here, but I thought it was important to kind of understand specifically what they're saying. So this is what the book says. It says, the entropy change of the water depends only on the initial and final states of the system, no matter whether the process is reversible or irreversible. We can imagine a reversible process in which the water temperature is increased in a sequence of infinitesimal steps delta t, dt. So this would be the idea that we go from 0 to like 0.1 degrees Celsius to 0.2, and then from 0.2 to 0.3. And in doing so, we call that process reversible. None of the processes themselves are truly reversible, but it's just the idea that as long as we make it an infinitesimal change of temperature, then we're fine. And then what we would need to do is to add up every single one of those changes in Q, those dQs that come into the system. And of course we do that by integrating, right? Heating the water on a stove whose cooking surface is maintained at 100 degrees Celsius would be an irreversible process. The entropy change, though, would be the same. That's the key thing to understand here. So for this one, we're going to have to say that delta S, the change in entropy, is going to be equal to the integral now of dq over t. See, this whole language of saying that we make sure every step is reversible and we only use infinitesimal steps dt, it's really just another way of saying we're going to do an integral, right? I mean, this is a complicated and long-winded way of saying you do an integral. That's all that they're saying. Because an integral will take into account all of the little changes. And you want to compare this to what you learn in calculus, the idea is that what they're saying with these infinitesimal steps is we're basically just doing a Riemann sum, right, where we make sure that the steps are very small. For this one, what we're going to need to do for dq here, we're looking at water that's heated from 0 to 100, so can anyone guess what dq might be in that case? Now, they gave us specific heat, so that should be a hint, right? What would dq become?
Isn't it MC dt?
That's right. So it's going to be MC, and then instead of delta t here, it'll be dt, because we're looking at infinitesimal temperature changes, right? And then that's divided by t. And then we would need to go between our initial temperature and our final temperature. So in this case, that's from 0 to 100, except we'll have to convert it, of course. So what we're going to get is the integral from 273 Kelvin up to 373 Kelvin of MC dt. So M is 1 kilogram. C is 4190. And temperature is a variable. So what we'll get is delta S is going to be equal to 4190 joules per Kelvin. The kilograms cancel out, and it was just 1 kilogram after all. Times the natural log. See, these logs, they always seem to show up, these entropy things. 373 over 273. And we can write the units in here, but they're of course going to cancel. So that should be equal to then
1,307 joules per Kelvin. Or it's roughly 1,300.
Yeah, I agree. 1,300 or so. 1,307. So this problem is good to kind of identify that when we say that you need to invent a path, as I was saying earlier, by which there's some kind of reversible system here, the integral kind of just does it for you, basically, in these kind of simple problems. Like, it just says make sure you integrate. Okay, don't just say that delta S is equal to delta Q over T, because then you'll get the wrong answer, right? Because if we just did delta Q over delta T, what we would get would be MC times delta T divided by the temperature, and this is not equal to what we got, which was basically MC times the natural log of like T2 over T1, right? So this might give you an approximation. What do you get if you do the left-hand side? Let's see. So you would get 4190 times delta T, which is 100, divided by T. Now, which T do you use? Use the final temperature, I guess?
What T would you use?
Yeah, so I don't know. Maybe you use the final temperature. If we use the final temperature, you get 1123. And if you use the initial temperature, you would get... I think final temperature makes sense, honestly, but neither makes sense. It's just, it doesn't work is the point. But if we use the other one, 4190 divided by 273, well, we get 15. Now, it turns out it's not even in the range. Right, so... Wait, did I sound wrong there? 4190? Oh. Times 100. Okay, that makes... I was going to say, it should be close to, like... So you would get a range on this one, depending on what you picked, of 1123 or 1534. Which is obviously not equal to 1307. But I'm wondering what's the average of that? Let's see.
Average is 1,329.
Pretty close, actually.
Yeah, it's close.
The average is actually pretty close. And that actually should make sense, because, well, yeah, I mean, if you take the extremes, then the actual answer should be somewhere in between.
It's because it's a continuous change.
Yep. Exactly. That's right, because it's continuous. That's exactly right. Yeah, because this is a... Okay. Anyway, let's keep going. Most of these entry problems are pretty short, luckily. Okay. Entropy change in a free expansion. Okay, partition divides a thermally insulated box into two compartments, each of volume V. Initially, one compartment contains N moles of ideal gas at temperature T. The other compartment is evacuated. We break the partition, and the gas expands, filling both compartments. This is a common thing we've seen before. This is what we call free expansion. What is the entropy change in this free expansion process? All right, there's the picture going from A to B, free expansion. Picture C is the free expansion process doesn't pass through equilibrium states from A to B. However, the entropy change SB minus SA can be calculated using the isothermal path or any reversible path from A to B. Okay? So they choose an isothermal path along which the temperature is constant, and that's the picture right there. We know we're going from a volume of V up to a volume of 2V. Okay. So how are we going to calculate this one? So what we have is our general definition of what entropy is, right? And that it is equal to dq. Oops. Now, in this case, the temperature is constant, right?
Yes, the temperature is constant. Oh, but the heat.
Which means it's isothermal, right?
Yes, isothermal.
So that means the dq is equal to dw, right?
Yeah.
And dw is equal to pdv. And then, you know, we just kind of do the same thing that you do a lot with these problems, right? nRT divided by vdv. Just chug all that inside of here. So what we'll end up getting is the integral of nRT over v, and there's a t that comes from the integral itself, and then there's a dv in here now, and we're going from a volume of v to 2v, so we end up getting that delta s is equal to, the t's cancel out, so we get n times r, and then we have a natural log of 2v over v, the v's cancel in, so you get delta s is equal to nr times the natural log of 2. Number of moles. So if, for example, we pick some values and we said, like, let n be equal to 2 moles, then we would get delta s would be equal to 2 times 8.31 times the log of 2. So it's going to be like 16, it's going to be like something like 14 or something like that. Let's see. because log 2 is about 70%. So it's 2 moles times 8.31 times natural log 2, 11.5. So this is 11.5 joules per Kelvin. Not a very substantial entropy increase compared to what we saw in the previous problem, but after all, in the previous problem, there was a massive temperature change involved because you're going from 0 to 100 degrees. And in this problem, it's probably to be expected that the entropy change is not very big. You've doubled the kind of size of where the objects can move, but you didn't increase how fast they're moving or anything like that because the temperature stayed the same. So there we go. You have any questions? Is there one more? Yep, here we go. Okay. Suppose that 1 kilogram of water at 100 degrees Celsius is placed in thermal contact with 1 kilogram of water at 0 degrees Celsius. This is kind of similar to the problem we did earlier, except it's not. I mean, the previous problem we did, water goes from 0 to 100 now. What we have now is you have two systems, right, that are placed in thermal contact with each other. So we've got our water that's at T equal to 0 Celsius, and we place it into contact with hot water. We'll just put them in contact with each other like this so that they don't necessarily mix, but they're touching each other. And just say, now we've got water here. It's hot, and this is at T equal to 100 degrees Celsius in both cases. And we want to find the total change in entropy, and we want to assume that the specific heat of water is constant at 4190 joules per kilogram. Joules per kilogram to Kelvin. How are we going to do this? So we use MC delta T again?
MC. Well, it's not isothermal anymore. Placed in thermal contact.
We know what the final temperature is here, right?
Yeah.
Like, I don't need to do like a calorimetry problem to figure out. We know that the final temperature is going to be 50, right?
Mm-hmm.
So this is the process. We start from here. We go to here. And what's going to happen at the end is they're both going to have the same temperature, which is going to be 50. Wait a minute. Am I wrong about that? Do we actually need to do the process?
Oh, wait.
It should be, right? If it's...
Not at steam. It's not steam.
No. It's all water. It's all water.
Okay.
Do we need to go through and actually do the calorimetry equation? What would it be? I mean, it's pretty easy to see what this is going to be. So you're going to basically have your Q hot plus your Q cold, and that's going to be equal to 0.
0,
and
yes.
It's going to be MC times it's final minus initial, right? So T minus 100 plus MC T minus 0, right? Equal to 0. All the MCs cancel.
Get 2T equals 100, and then so T equals 50.
Yeah. Okay. Just to make sure. Okay.
Yeah, it's all good.
All right. So basically, what's going to happen is you're going to have a delta S for the colds, and you're going to have a delta S for the hot, right?
Okay.
And the only difference is going to be that this one is going to go, for the hot one, it's going to go from 100 to 50, but really not 100 to 50. It's going to go from 373 to 50 minus that, or 323. Ugh. Why can't I just write when I'm talking without making mistakes like this? Okay, 373, 323. Those are both going to be in Kelvin. And then on this one, we're going to be going from
273 to 323.
Now, before we do this, I want you to think about something. Do you think you're going to get the same answer for both of these?
I think, okay, before I do it, I think I'm going to get the same answer in magnitude. Like, it'll just be a negative, a difference of a minus sign.
Okay, let's see. All right, so the left side here for the colds, what we're going to do is we're going to say delta S for the colds, water, is going to be equal to the integral from 273 to 323. dq, again, we'll use mc times dt over t. So this is going to give us mc times the natural log of 323 over 273. And that's going to be delta S for the colds. So we plug in the numbers here. It's 1 kilogram. It's 4190.
Oh, yeah.
What do you think now? Do you think that they're going to be the same?
Well, now that I remember that, it's a ratio instead of a difference.
Yes, exactly.
Then it's definitely going to be different.
Definitely, yep, exactly. So we get that for delta S colds, and then we can skip through those steps for delta S hot and just say delta S hot. We basically just do the exact same thing, except we put the limits in differently. This one I messed up. I made a typo when I went down here. That should have been a 2, in case you didn't notice that I just did that. Okay, and then delta S hot will end up being 1 kilogram, 4190, and then natural log of, this case, 323 over 373.
For the delta S hot, you get negative 603. And the cold, you get 704. Or 705. Oh, yeah, okay. Also, the change in entropy. Okay, so entropy is always increasing. It looks like.
Even though in one part of the system the entropy went down, and that makes sense. The entropy of the hot water should go down, right? It cooled off, right? That's logical. That the entropy went down for the hot water. So you got to be really careful about the statement that I said earlier. It's not that entropy increases everywhere. It's that when you take the whole system into account, that the total entropy is what's going to change, or that the total entropy is what's going to increase. So delta S cold, in this case, you end up getting a positive 70705 joules per Kelvin, right? So kind of the net change.
Yeah, we got a net change of like
about
102.
Yeah, so if you take delta S cold and we add that to delta S hot, it's about 102 joules per Kelvin.
Wow, that's crazy.
Yeah, so this proves in a very simple system that entropy always increases, right? Even though part of the system becomes more ordered, the other part of the system becomes more disordered at a higher level, right? Now, you can, of course, come up with systems yourself if you want to where the total entropy change is 0, but you will never find one in which it's negative when you take into account everything. And if you do find that it's negative, then you must not have taken something into account, right? There's a nice picture in the book of a dog eating like puppy chow or whatever, and it says that, if you're growing as a human being or a dog or anything, you ingest food, right? And then by ingesting that food, your body basically turns that food into more organized molecules, proteins, and whatever, all the stuff that happens biologically there, right? So that process of you growing up, into to some extent, is a process that is making you more organized molecules and things like this. But there's all kinds of other things that happen as well, because you eat the food, you digest it, then you excrete it. That's an increase in entropy process. You also, your body's heating up through this process as well. So when you take everything into account, any system that you can think of, entropy is increasing. I think that was the last of the problems. So what we'll do now is we're going to talk about a microscopic description of entropy. I don't know if I can get through all this stuff. And I almost feel like if I just show you the video, that it's going to explain it better than I am. But I'm going to at least give it a shot of setting it up for you, and then we'll watch the video. So here we go. This is the picture we want. You'll notice we're going to come back and do this same question we did again. All right. Okay. Come on. Oh, I think it's because I'm touching the... Why can't I just get it to... Okay, click. Click. Boom. Okay. All right. So here's a picture of some coins. Why are we talking about coins? We're talking about coins because entropy is about randomness, and coins are random. Okay, so we want a microscopic description of entropy. We want to understand what entropy means at a molecular level, basically. All right? So, suppose that we toss some coins. All right? And suppose that we toss n coins. All right? And these coins are identical in every way. They exhibit true randomness. After tossing them, let's say that what happens in the final state is we get an equal number of... Baron said farts equal chaos. Yeah, that's right. There you go. That's great. I like that. Okay, toss in identical coins, and let's say that what happens is that half of the tails end up heads, and half of the tails end up tails. Okay? Let's say that's what happens. So you toss like 6 coins, and like 3 are heads and 3 are tails, all right? So... the result in one case is that you get half heads, half tails. This would be the most probabilistic outcome, although it's not guaranteed to be the outcome. This would be what we call the macroscopic state. I'm just going to call it the macro state. But by macro, I mean macroscopic, so I'll put a little dot there. This is the macroscopic state of the system. Is my system of n coins resulted in half heads and half tails. That's the kind of macroscopic state, right? To compare it to gases, that's like pressure, volume, temperature, all right? The individual information about each coin is the microstate, right? Okay, so the individual info on each coin is what we call the microstate. Microscopic state, so I'll just put microstate. Okay, so half heads and half tails, you'd ask, well, how did it come down? Because here's an example of, this is an example of every single possible macroscopic state, okay? The macroscopic states are on the left, so 4 heads would be one possible macroscopic state. There is only one possible microstate for that. That is, all 4 are heads, right? Again, the individual information about each coin is what we call the microstate. If the result that you get is 3 heads and 1 tails, that's one possible macrostate. But how many ways can you have 3 heads and 1 tails? Well, you could have the first 3 coins flip heads, and then you get a tail. You could get 2 heads, a tail, and then a head, a tail, head, a tail, a head, right? So these are 4 different microstates that correspond to the same macroscopic state, right? From a macroscopic perspective, these are all the same. From a microscopic perspective, they are not the same, right? They involve a different ordering in which the coins flipped, right? Another possibility, 2 heads, 2 tails. You figure out that you get exactly 6 states there, and you kind of just have to work out individually what each of these would be, okay? And you can do this for yourself, and you just got to make sure you count up everything, right? But here you get this kind of big picture here of microstates is what how the individual coins kind of were ordered as they landed, and the macroscape is the kind of thing that combines them all. Because after all, the one thing that these 6 microstates have in common is that they would all be categorized as 2 heads and 2 tails, right? Okay. Now that we know what those things are, okay, we can say that in general there can be many microstates that correspond to the same macrostate. As I said, for n equal to 4, there's 6 possible states with half heads and half tails. The number of microstates, we'll play it this way, the number of microstates grows rapidly with n. Okay. How many total microscopic states do we have for 4 coins? It's a lot, right? Let's count them up. There's 4 here, there's 4 there, that's 8. Plus this and this, that's 10. Plus this up to here, that's 16, right? Right, so you get 4 and 2 is, sorry, 4 and 1 is 5. 4 and 1 is 5, that's 10, and add the 6 in here, you get 16, right? So it turns out that for n equal to 4, the number of microstates ends up being equal to 2 to the 4, which is equal to 16, right? So now, if you have, for example, if m was equal to 100, okay, then the number of microstates is 2 to the 100, okay? So then 2 to the 100 is about equal to 1.01, 1.27, sorry, 1.27 times 10 to the 30. And then if you go to work out how many of wait, what do I want to say now? Yeah, 2 to the 100, this is the number of microstates. And out of these, 1.01, these numbers are just insane, times 10 to the 29 are heads, whoops, are half heads, half tails, right? So here's where we connect this all back to probability. So if I want to know the probability when I toss 100 coins of getting half of them being heads and half of them being tails, you count up all the possible ways that you could get half heads and half tails. And with 100, you can imagine it would take some time to count all of this stuff up, right? Because it could go, you could get 50 heads in a row and then 50 tails in a row. You get 50 tails in a row and then 50 heads in a row. You could get 1 heads and then 49 tails and then 49 heads. You get the idea that there's a lot of states, and it's about 1 times 10 to the 29, right? If you want the probability of this result occurring, what you have to do is you have to take this number, which is the macro state, and you need to divide by the total number of microstates. All right? You need to take the number of possible ways in which you can get half heads and half tails and divide by all the possible combinations, which is this 10 to the 30 number. So you would get this divided by this. The least probable outcome would be all heads or all tails, right? Let me ask you this question so you can understand what's going on here. If I flip 100 coins, how many possible microstates would there be that include all heads? Is it 1 microstate? Is it 2? It's 1, right? That's 1 microstate. 1. So the odds of that occurring are basically impossible. The odds of getting all heads would be 1 microstate divided by the total number of microstates. So a 1 in 10 to the 30. You could start doing this, flipping 100 coins, and you could do it every day for your entire life. And even if you lived to be even if you started this at the beginning of the universe, you still wouldn't finish. You'd never get this result. Or you might get it, but it'd just be really, really unlikely, right? So 1 in 1.27 times 10. It's worse than your odds of winning the lottery. You're better off. It's easier to win the lottery than it is to flip 100 coins in a row and get all heads. Or all tails, for that matter. Right? Okay. So, in general, the most probable state is the one with the most microstates. I.e., in this case, that would be half heads and half tails. Even though, I almost guarantee you can try this experiment yourself if you want to. You can go and take a coin and flip it 100 times. I know that's going to take a long time. And you mark down heads, tails, whatever you get each time, right? Chances are it's probably not going to end up as 50-50, right? Just because it's the most probable does not mean at all that it will be the one that you get, right? You all understand that? In fact, I think there's only a 10% chance or so, right? You can figure out pretty quickly by taking this number, the number of possibilities of the ways you can get it, like the odds. So the odds of the half and half, so 50-50, the odds of that would be 1.01 1.01 times 10 to the 29 divided by 1.27 times 10 to the 30. And that's about 10%, right? A little less than 10%. It's probably something like 9%. You can calculate it if you want to. So even though there's only a 9% probability of that happening, it is still the most probable outcome, right? Let me ask this question. If I take 2 dice, 6-sided die, and I roll them, what's the most probable outcome? Does anyone know? 2 6-sided dice, and you roll them. What's the most probable outcome?
Are you asking for like the specific numbers on the die?
Yeah.
Oh my.
What's the outcome for the final? Is it 6, 7, 8, 9, 10? What's the most? I'll ask you this question. If I take 2 dice and I roll them, what are the odds of getting 2? So that one's a 1 and one's a 1.
Adding them.
What are the odds of this as my final state? You'd have to think about how many ways can you get a 1 and a 1. Rouge has got the answer. The answer is 7. That's right. The most probable is 7. But how do you figure that out? It's the same way, right? So a 1 and a 1, right? The odds of getting a 1 and a 1, you have to think about what is the total number of microscopic states that you can possibly get. And the answer is going to be 36, okay? You can get 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Then you can get 2, 1, 2, 2. You go through all the possibilities, you add them up, you're going to get 36. It's 2 6-sided die, 6 times 6 is 36, right? This happens 1 out of 36 times. You get a 1 on the first die and a 1 on the second die, right? If I look at 6, 6, or what they call boxcars, right? The odds of this are 1 in 36 because there's only one microstate, which is the 6, 6, that corresponds to this. And this is true for any of the doubles. So 2s, 5s, 3s, whatever. Any doubles will always be 1 in 36. 7s, on the other hand, to get a 7, there are many ways to do this, right? I'm not going to write the dots for these. I'm just going to write numbers, right? You could have a 1 and a 6. You could have a 6 and a 1. You could have a 3 and a 4 and a 3. You could have a 2 and a 5 and a 5 and a 2. These are all, even though 2 and 5 and 5 and 2 give you the same number, they do represent unique microstates, right? So did I get them all? 1, 2, 3, 4. Yeah, we got them all there, right? So then this has the odds of this happening then there's 6 states, right? Out of a total of 36. So the odds of getting a 7 are basically 1 in 6. That seems low. Is that really what the answer is? I guess that's the answer. What about another number? Can we prove that that's actually the largest one? Let's try 6. 6 is going to be what? It's going to be 3 and 3. It's going to be 1 and 5. It's going to be 5 and 1. It's going to be 4 and 2. And it's going to be 2 and 4. I see 5 here. So this is going to be 5 out of 36. This can't be reduced. But it is nonetheless slightly smaller than 1 out of 6. Therefore, this is the most likely number. You can argue that the same thing for 8. You'll get 5 out of 36 for 8. But yeah, that's the odds of rolling a 7, 1 in 6. Again, you roll 2 dice. This is the most probable outcome. It does not guarantee when you roll the dice that's the outcome you're going to get, though. Right? All right. I didn't even get to the part where we tie this to entropy. So it turns out that this state, the half-heads and half-tails state, contains the most randomness. And that's how we tie this back to entropy. Now, why do I say it has the most randomness? It has the most randomness because the total number of microstates is the largest. There are the largest number of ways that you can take half-heads and half-tails compared to the other ones. Just like the odds of rolling the 7 have the most states. The most states means it's more likely that it's going to occur, right?
Yeah. Yes.
Does this all make sense to y'all? Okay.
Mm-hmm.
So, I bet that's it. That would be the state that has the highest entropy.
Be the most probable. Oh yeah.
Okay. So let's think about this in terms of gas molecules. If we consider a gas, with 1 mole of molecules undergoing free expansion. The macroscopic state is the pressure, the volume, and the temperature. Okay? Yes, 7 would have the most entropy, and therefore be the most likely. Yeah, this would have the most entropy. That's right. So we consider a gas with 1 mole of molecules undergoing free expansion. Pressure, volume, and temperature are the macroscopic state, and the microscopic state would be the position and the velocity of each particle. And in a free expansion, the range of the microstates increases, so the entropy increases, right? I'm going to write all the things I just said down. Okay, so take a gas, 1 mole of gas. So macro state is pressure, volume, temperature, right? But the temperature, the volume, and the pressure, you could have the same value of these things with all kinds of different organization of the molecules within the room. So the microstate is position and velocity of each particle. And in free expansion, the number of microstates increases, so the entropy increases. So if we think about the volume doubling, for example, microstates increase because there's just more places for the molecules to go. And to kind of tie this back to probability, so in any thermodynamic process, the most probable macroscopic state has the highest number of microstates associated with it. And that also means it has the highest entropy. So, if we can actually count the number of microstates, okay, then we let the symbol W represent the number of microstates. And then the entropy of a state is equal to the Boltzmann constant multiplied by the natural log of the number of microstates. And that is the microscopic definition of what entropy is. In principle, we could also add a fixed constant to this, but by definition, we make the constant 0, and now delta S is going to be equal to K times the natural log of W2 divided by W1. And that's the microscopic definition of entropy. Anyone have any questions? It's all about probability, 100%, completely about probability. Now, since it's probability, you can calculate the probability that things that are really unlikely will occur, right? Even though it is not likely that you could flip 100 coins and get all of them being tails, it does not mean it's impossible. It just means you would need to repeat the process a lot of times before you ever got to it. And you'd probably get a lot of situations where you got like 80 tails and 20 heads and maybe 60 tails and 40 heads. Can you use statistics to quantify entropy? We can. Absolutely. This is the statistical definition of entropy. That's right, Ruja. So in upper level physics classes, they refer to thermodynamics. Instead of calling it thermo, you take a course that's called statistical thermodynamics, where you apply statistics to thermodynamic systems, right? And then the course you take after that is what's called Statistical Mechanics, which is more on the same topic, basically. But yeah, you can absolutely use statistics to quantify entropy, and that is the way in which we describe these type of systems. I'm going to go ahead and show you this video. It's going to go a little bit over class time, but I'm pretty sure it ends like here or something like that, so it's really only 10 minutes long. I'll put a link in the chat so you can watch it yourself in case you want to watch it on your own time and you need to go. But it's a pretty good description of entropy, but it also goes into some of the things that are not true about entropy that you might think. Yeah, so we're just gonna watch this video. And if you have any questions, please let me know. I need to switch screens so you can actually hear it. Change windows. Screen. No, applications. This one. This one. Let me know if you can't hear anything. If you can hear it, then we're good.
Thank you to Brilliant.org for supporting PBS Digital Studios. Entropy and the second law of thermodynamics have been credited with defining the arrow of time, predicting the ultimate heat death of the universe, and providing the driving force for the development of structure as well as decay, and also excusing the messiness of your room. But what is entropy really, and how fundamental is it to our universe?
Disney Plus, Hulu, and ESPN Plus now bundled together. The greatest.
I'm sorry.
Entropy is surely one of the most intriguing and misunderstood concepts in all of physics. The entropy of the universe must always increase. So says the second law of thermodynamics. It's a law that seems emergent from deeper laws. It's statistical in nature, and yet may ultimately be more fundamental and unavoidable than any other law in physics. Einstein said that the thermodynamics that encapsulates the second law is the only physical theory of universal content which I am convinced will never be overthrown. And the great astrophysicist Sir Arthur Eddington warned, "If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation." We've looked at entropy in the past, but it's time to go much deeper, to unravel the great unraveler. Over some upcoming episodes, we'll explore different aspects and consequences of entropy, including its role in black hole thermodynamics and how it will lead to the end of our universe. But today, we'll see what entropy really is, and why the second law of thermodynamics is considered to be so fundamental and so unavoidable. Let's start from the beginning. In 1824, Sadi Carnot published his Reflections on the Motive Power of Fire, in which he revealed the theory for perfect engine efficiency. Heat engines, which in Carnot's day were the newfangled steam engines, work by turning the flow of heat energy into mechanical energy. For heat to flow, you need two reservoirs of different temperature. A perfectly efficient engine, one undergoing the Carnot cycle, converts all transferred heat energy into useful work. In principle, that work can then be converted back into heat, and so the temperature differential can be re-established. However, an inefficient engine will slowly deplete the difference in temperature, reducing the heat flow, and the engine winds down. Around a half century after Carnot, Rudolf Clausius was inspired to quantify this tendency of heat energies to decay over time. Enter entropy. Clausius defined entropy as the internal property that changes as heat energy moves around within a system. Specifically, the change in entropy of each reservoir is the heat energy going into or out of that reservoir divided by its temperature. For a Carnot cycle, the overall change in entropy is zero, but for any less efficient cycle, entropy increases. In fact, an increase in entropy means that the heat reservoirs are approaching the same temperature, reducing their capacity to do useful work. Carnot and Clausius's work revealed entropy as a measure of how evenly spread out a system's energy is. The more evenly spread, the less useful the energy is. And for an isolated system, the best you can hope for is that the separation of energy and the entropy remain constant. In reality, it will almost always increase unless energy comes in from the outside to re-establish the temperature differential. This understanding of entropy is in terms of flowing heat, and it came from the days when many, including Carnot himself, believed that heat was a physical fluid called caloric. It took a revolution to understand the reality of entropy. That revolution was statistical mechanics, founded by the great Ludwig Boltzmann with his kinetic theory of gases. This theory explained thermodynamic behaviour as the summed result of the individual motion of tiny particles under Newton's laws of motion. Stat Mech is really astounding. It's founded on an absurdly simple idea. For a given set of large-scale observable properties, every possible configuration of particles that could give those properties is equally likely. Let's add some physics speak. By configuration, I mean the exact arrangement of positions, velocities, etc. of all microscopic particles. We call this the microstate. And we call the specific combination of large-scale macroscopic properties the macrostate. Macrostates are entirely defined by thermodynamic properties: temperature, pressure, volume, and number of particles. For a given macrostate, all microstates consistent with its thermodynamic properties are equally likely. For some macrostates, there are lots of different microstates, or arrangements of particles, that lead to roughly the same thermodynamic properties, while other macrostates can be produced by only very few microstates. Okay, one more fact. If you leave a system to do its own thing, it'll eventually try out all possible microstates that are possible given the laws of physics. All particle arrangements will eventually happen. So, if you look at the system at some random point in time, it'll be in a completely random microstate chosen from all possible microstates. And what macrostate will it be in? Well, probably the one that's consistent with the most microstates. We can think of these micro and macrostates with an analogy. This is a Go board. Let's say you place 180 black stones at random. Every possible specific arrangement is considered a microstate, while the overall shape of the distribution would be the macrostate. There are nearly 2 times 10 to the power of 107 ways to arrange the pieces, and almost all of them are pretty evenly mixed, so roughly all the same macrostate. Some microstates are weird though, and they give different macrostates because they're different average distributions. For example, there's one where all of the stones are on one side. That microstate is a factor of 2 times 10 to the power of 107 less likely than one of the many smoothly mixed microstates. And the larger the board, the less likely it is to end up in such a weird arrangement. For a room full of 10 to the power of 26 molecules of air, the chance of getting all of the air molecules on one side of the room by chance is so small that it never happens. We've been talking a lot about particle position, but really that Go board is an analogy for all possible combinations of all properties: position, momentum, spin, vibration, really any degree of freedom that the system can have. We call this space of properties a phase space. And instead of particles being distributed through position space, a microstate is really defined by how energy is distributed through phase space. The average distribution of individual particles in phase space defines the thermodynamic properties of the system. That's why these similarly shaped distributions on the Go board correspond to the same macrostate, while the clustered spread does not. Okay, so if you leave a system alone long enough, its particles and its energy will find its way into all the different forms that are possible. The vast majority of possible distributions of energy leave the system very close to a single macrostate. That's the state of thermal equilibrium, in which energy is maximally spread out, and temperature, pressure, density, volume, etc. have the values we expect from classical thermodynamics. Statistical mechanics tells us why large-scale systems have the properties they do. But what does this have to do with entropy? Well, Ludwig Boltzmann figured that out too. The Boltzmann equation tells us that entropy is the logarithm of the number of microstates consistent with the current macrostate times the Boltzmann constant. So our smoothly spread out equilibrium Go board has a high entropy, and our clustered board has low entropy. By the way, there are certain special microstates, special arrangements of particles that look highly ordered but are still consistent with our high entropy macrostate. For example, if we try to draw pictures or write words in phase space, this is where we get to a point of common confusion. Order is not the same thing as low entropy, and the second law isn't always the tendency towards disorder. In thermodynamic entropy, the only special arrangements of particles that change entropy are the ones that change the thermodynamic properties, not the ones that spell out cuss words or mess up your room. To get deeper into that, we'll need to talk about information entropy, which we'll also need for black hole thermodynamics, and will take another episode. Okay, so the macrostate that defines thermodynamic equilibrium is by definition the one with the most microstates, which also means the maximum entropy. Any system not in equilibrium must increase in entropy simply because at any future time, its current microstate will most likely be one of the more common types of microstate. This is assuming you don't force the system from the outside. It's possible to take each glowstone and place it on a particular spot to construct a special microstate, or to use a vacuum pump and a glass wall to move all of the air to one side of the room. In both cases, you're reducing the number of accessible microstates, which by definition must reduce entropy. But to do so, you must introduce an external source of energy. Heat must flow between your system and the outside universe in a way that increases the entropy of the universe as a whole. Statistical mechanics inevitably leads to entropy and the second law, and it does so by something so fundamental and basic that it's impossible to deny. It comes from counting the ways that energy can be distributed. The inevitability of the rise of entropy is as fundamental as counting. That's why Einstein and Eddington were so sure of it. But entropy is also statistical and emerges from the behavior of particles under the laws of motion. This is where the second law appears to add something new to the universe, not seen in the more fundamental laws. It seems to add the arrow of time. See, the laws of motion, whether Newtonian or quantum mechanical, don't care about the direction of time. And yet the second law of thermodynamics clearly distinguishes between the past and the future. We talked a little about this in our episode on the physics of life, where we saw how entropy drives both the increase and decay of complexity. It's almost like the concept of time is emergent and statistical, just like entropy. Again, we'll delve deeper into this in the future, but for now, please be careful to keep your number of accessible microstates low, avoid thermal equilibrium, and keep being that brilliant macrostate that is you until I see you next week on Spacetime. The field of statistics.
Okay, there we go. I don't know what you guys thought about that, but I really like the idea that entropy and the second law of thermodynamics basically give you a direction to the way in which systems have to evolve, and thereby, tell us that time can only go in one way. So, yeah. Any questions or thoughts?
So it kind of like it defines the direction of time.
I mean, to some extent, yeah. I mean, the fact that there are certain processes that you would never see happen in the opposite direction implies that kind of the direction the processes evolve is related to direction in which time moves, right? I mean, he mentioned that the other physical laws don't incorporate time. I mean, gravity can be used to describe the motion of the planets forwards and backwards, right? If you took a video of the Earth orbiting around the sun, and you ran that video in reverse, you wouldn't violate any laws of physics at all, right? It would just be that the velocity of the object is just going the other way. And nonetheless, Newton's laws of gravitation or whatever laws you want to use would still describe the system. But you cannot do the same thing when you talk about thermodynamic systems, right? So again, going back to this picture right here, you can reverse the video of a firecracker exploding, but then there's all these unphysical things happening that you will know, you as an individual, whether you're a scientist or not, you'll look at that and say, I know that's a video running in reverse because I've never seen a firecracker do that before. I've never seen anything do that before. I've never seen little pieces of paper that have been cut up, turn into a big piece of paper. I've never seen a fluid spontaneously undissolve itself. You don't see those things happen. And so when you're thinking about why you don't see them happen, well, there's a fundamental law that describes it. And that fundamental law is connected to your experience of time, your experience of the ordering of time, right? Of what comes first and what comes next, of what the cause is and what the effect is. And in that sense, entropy, the second law, arrow of time, they're all kind of jumbled together and they can't really be separated, so to speak. I'm going to go ahead and stop the recording for now, but I will take other questions if you have more. Next week, we're going to talk about waves